Good morning, Algebra 2. So I'm pretty sure that your notes don't have this problem on it. I hope you watched the video where I filled out this table, but I kind of want to talk to you about this table for just a moment before I get into the notes. The problem says investigate the growth of a $1 investment that earns 100% annual interest over 1 year as the number of compounding periods per year in increases. So you might remember that we have learned compound interest, and it's this formula right here. Remember, P is your principal, that's how much money you're investing. R is your rate. We're typically given a rate as a percent, and we have to change that to a decimal. N is the number of times that it's compounded, and that's where these words come in. Annually means 1, semi-annually means 2, quarterly is 4, monthly is 12, daily is 365. You're probably not going to be using these last two, but for our purposes, I did use it for this particular problem. And then T is how many years, so your time in years. So this particular problem, we're investing $1, so that's our P, at 100% annual interest rate. So you'll notice I took the 100%, I moved the decimal point over 2 places, it was behind the last zero, moved it over 2 places to the left. That gives me a value for R of 1, and this is occurring for 1 year, so my value for T is 1. So those 3 values were the same throughout the entire problem. P is 1, T is 1, R is 1. But what changed was our values for N, those numbers right here, depending on how many times we were compounding. So based on this, here's what I want you to look at. This is kind of an investigation right here. Let's look at our values. We start off with 2, then we go up some more, and we continue to go up. But you see, as we get towards the end, as these numbers for N continue to increase, and they certainly have gotten larger, starting all the way at 1 and ending up at 31,536,000. So they've increased significantly. But you'll see that this number, it continues to go up, but not by a whole lot once it starts. As these numbers get bigger, you see some digits that kind of stay consistent. At 2.718. So that brings us to the number E. Now you might be thinking to yourself, E is a letter, it's not a number. Well, you're both right and wrong. E is a letter, but E also represents a number. It is an irrational number used in math, kind of like pi. Pi is 3.1415 ... That's also an irrational number. E is also an irrational number, which just means that it can't be written in the form of a fraction. So E is this number right here. And obviously it continues forever. Now the reason that it's called E is they named it after the person who discovered it, Leonard Euler. So it's called the Euler number. But they use E just to, because he's the one who discovered it. Now if you have a calculator, because at some point you're going to need a calculator, you see that there is an E button on here. Now my calculator, it's right here in green. Can you see that? Right above this button that says LN, it's right here. So if I hit the second button and I hit that, and right away it shows that it's going to do an exponent. If I were to just plug in a 1, just saying I'm raising it to the first power, so I just want a plain E. There's all those digits. Now it doesn't show as many digits as what we know the number actually is, but it does a pretty good job. Notice that 2.718 is there, which is what we saw in our investigation over here. We saw those digits continue to show. Actually 2.7182, it continues to show. So that is the number E. All right, so for the first few examples, what we're actually doing is using our properties of exponents that we learned all about in a previous chapter. So let's take a look at number 1. It says e to the third times e to the fourth. So remember our rule, if the bases are the same and we're multiplying, the rule says that we're going to add the exponents. And so 3 plus 4 would give us 7. So we would have e to the 7th power. And that's all we need to do. We don't need to plug it into the calculator to find out what that equals. We're just going to leave it e to the 7th power. Now, example number 2, we're not multiplying, we're dividing. So first I'm going to take a look at the coefficients. I have a 10 divided by 5. 10 divided by 5 is 2. Then I'm going to look at the e's. The rule is different for division. It says if your base is the same, you're going to subtract your exponents. So we're going to do 3 minus 2. So our final answer is going to be 2e to the first power. You don't have to write that first power. It's understood to be there. If you want to write it, you can. All right, number 3. We have 3e to the negative 4x power squared. All right, remember we learned that if everything in the parentheses is either multiplication or division, you're allowed to take this exponent and it has to go to everything on the inside. So it's going to go to the 3. It's also going to go to the e to the negative 4x power. So here's how this looks. I have 3 squared, and then I have e to the negative 4x power squared. 3 squared is easy, right? It's going to be a 9. Here we're going to do a power to a power. That means we multiply those together. So we keep our base of e. We're going to multiply negative 4x times 2. That gives us negative 8x. It's looking pretty good, but it's not the final answer because remember, we don't want to have negative exponents. How do we get rid of that? Remember, we're going to take this. Right now it's in the numerator, right? Because there's an understood 1 down here. We're going to move it to the denominator. And when we do that, it's going to change the negative 8x to a positive 8x. Now, why didn't we move the 9? Well, the 9 didn't have a negative exponent. The negative exponent is only touching the e. So that's the only thing that gets to move. The 9 doesn't have an exponent. It's understood to be an exponent of 1. And that's positive, so we're going to keep it where it is. So we end up with 9 over e to the 8x. All right, let's try a couple other problems pretty similar. Let's start with number 4. We have 24 e to the 8th over 9e. So I'm going to start with the coefficients, 24 over 9. 9 does not go evenly into 24. However, both of those numbers are divisible by 3, so let's reduce it. 24 divided by 3 is 8. And 9 divided by 3 is 3. Then with the e's, we're dividing. We're going to keep the base. We're going to subtract the exponents. There's an understood exponent down here of a 1. So we're going to end up with 8/3 e to the 7th. You're welcome to leave your answer like this. Some people might choose to write it 8e to the 7th over 3. It doesn't matter to me which way you choose to write it because both are correct. All right, number 5. So here we have a negative exponent on the outside, a little bit different from this one. Remember we learned in a previous chapter that we could go ahead and change that negative exponent to a positive exponent simply by flipping this whole thing. So in other words, I'm going to do 1 over. I'm going to take that whole thing, move it to the bottom, and it changes my outside exponent to a positive 3. So it doesn't change anything inside of the parentheses. That negative 5x remains a negative 5x, but it changes our outside exponent and turns it into a positive 3. Now I need to take that positive 3 exponent and it needs to go to the 2 and it needs to go to the e to the negative 5x. So 2 to the 3rd power, that's 2 times 2 times 2 is 8. Then we're going to raise e to the negative 5x to the 3rd power. That's a power to a power. That means you're going to multiply those powers. So negative 5x times 3 is negative 15x. Well, what's the problem? That negative exponent, we're not allowed to have it. So we need to move it. So because it's in the denominator, we're going to move it to the numerator. But notice that the negative 15x is only touching the e. So the 8 does not get to move, just the e's. So I'm going to have e to the positive 15x because I've moved it from the denominator to the numerator over 8. The 8 has to stay where it is. All right, number 6, again, we're multiplying. So the rule is you keep your base, you add your exponents, and so we're going to get e to the 15th power. So that's a good review of our properties of exponents. All right, now we have some radicals. So remember with radicals, whatever number the index is tells you how many you need in a group in order to take things out. So let's look at number 7. There's no index written there. That means it's understood to be a 2. Remember, if an index isn't there, that means that it's a 2. So let's talk about what we have underneath that radical with an index of 2. We have a 9. How can we break 9 down into prime factorization? It would break down into 3 times 3. All right, now let's talk about that e to the 2x. If I were to break it down, I would have e to the x times e to the x. Now, if that confuses you, let me explain it. Remember here, if the bases are the same and we're multiplying, you would add those exponents together. So x plus x, that's where the 2x came from. So I have the same base for each, and I have a total of 2 of them of the e to the x's. Now, according to this, our radical is a 2, so we want to look for groups of 2. Well, I have a group of 3's, and I have a group of e to the x's. That means I get to take out a 3 because I had one group. I also get to take out an e to the x because I had one group. And that also means that there's nothing left underneath the radical, and that is our final answer. So 3e to the x. All right, let's take a look at number 8. So our index this time is 3. So we're looking for, remember another way to talk about this is, what number can you multiply times itself 3 times to get negative 64? Well, that answer would be negative 4. So I'm going to go ahead and take out a negative 4. That just means that I was able to multiply negative 4 times itself 3 times to get negative 64. Now let's talk about this e to the 12x. And I'm going to show you a shortcut, but first I'm going to show you the long way. So this means that I'm going to have 12 of those, right? And it's going to take me just a moment to write them all down. All right, so here I have 12 e to the x's, and I want to put them in groups of 3. So I have 1, 2, 3, and 4. So I still have my negative 4, and now I'm going to take out e to the 4x. Why is it a 4x? Because I had 1, 2, 3, 4 groups of them. And I told you I was going to teach you a shortcut. And I have talked about this before, but you might have forgotten. It's been a little while. You can take your index and divide it into this number. 12x divided by 3 tells me that I can take out e to the 4x. That's a great tool so that you don't have to write these out every single time. So let's try that shortcut with number 9. First of all, our index is 4. So we're asking ourselves, what number can we multiply times itself 4 times to get 16? And hopefully you guys know that answer is 2. 2 times 2 times 2 times 2 is 16. But now I'm going to use the shortcut. 4 can divide into 8x 2 times. So I'm going to have e to the 2x. Isn't that so much faster? All right, so let's try our shortcut with the remaining problems. We have an index of 4. What number can we multiply times itself 4 times to get 81? That answer is 3. 4 divides into 12 3 times, so we're going to have e to the 3x. Next one. I don't see an index. That means that it's understood to be a 2. What number can I multiply times itself twice to get 49? That answer is 7. 2 divides into 18 9 times. So we're going to have e to the 9x. And then last one, we have an index of 3. What number can we multiply times itself 3 times to get 125? That answer is 5. 3 divides into 21 7 times, so we have e to the 7x. So if you can remember that shortcut, it really makes you spend a lot less time on those types of problems. All right, the last few examples that we're going to do require a calculator. Now, if you don't have a calculator, you probably have a cell phone. You can use your cell phone calculator. You probably have a calculator on your laptop. Any of those will do. I do have a calculator. So it says evaluate to 3 decimal places. So in other words, we're going to be evaluating to the 1,000th place. So we have to look at the 4th decimal place to determine how we're going to round. Remember, if it's 5 or higher, it rounds up. And if it's 4 or lower, it stays the same. So I need to do e to the 3rd power. So remember I showed you on my calculator where that button is, right there in green. So I have to hit second, e, and then I'm going to raise it to the 3rd power, just like that. Now let's look at what we have. We want to round it to the 3rd decimal point. So we have to look at the 4th one to find out what happens to the 3rd one. This is a 5, so it's going to round that up. So we're going to have 20.086. I'm going to use an approximate symbol. Why am I using an approximate symbol? Because we rounded. It's not exact. All right, let's take a look at the next one. Hold on just a second. I was trying to get my calculator better. Okay, so this time we're going to do 2 times e to the negative 0.53 power. Can y'all see that? 2 times e to the negative 0.53 power. Again, we want to look at the 4th digit. Our 4th digit is a 2. That means we're going to leave it the same. So we're going to say approximately 1.177. All right, next one, we're going to do e to the 4.8 power. Let's look at that 4th digit behind the decimal point. It's a 4, so we're not going to change the 0. So we're going to say that it is approximately 121.510. All right, only 3 more to go. Next we're going to do, let me just clear this, fresh screen, e to the negative 1/3 power. Negative 1/3 power. All right, 4th digit is a 5. That means that 6 needs to get rounded up to a 7. So we're going to say approximately 0.717. All right, almost done. Next we have negative 1.8 times e to the 4.2 power. So I have it plugged in just like I see it on my paper. The 4th digit behind the decimal point is a 3. That means the 5 stays as is. So we're going to say that this is approximately 120.035. All right, last one, y'all. We have 0.15 times e to the negative 6th power. 4th digit behind the decimal point is a 3. Ooh, well, it wouldn't make much sense for us to have 0.000, right? So let's round it 1 extra digit and we'll look at the 5th digit. The 7 is going to make the 3 go up to a 4. So we're going to say 0.0004. It would not have made a whole lot of sense to have 0.000 whatever. All right, so that takes us through part 1 of 8.3. Tomorrow we'll work on the second part. Your homework assignment for this is in the book. It's in RenWeb. You can check that out. Send that to me as soon as you can. And then tomorrow we will work on the second part. And then we're going to be meeting on Zoom on Friday. So I look forward to seeing all of your faces then. And until then, I will see you later.